All right, so we're going to start in chapter 1. So first we're going to define chemistry. What is chemistry? Okay. And chemistry is defined as the study of matter. And with the study of matter, we're going to try to understand the processes that matter is going to undergo, whether it's a physical process or a chemical process. And as it's going through those processes, the other thing we're going to study is the energy it gains or loses. Okay? So this is kind of what the overview of, a very simple overview of what we're going to try to accomplish in here. Yes?
Are your notes going to be online or on campus?
Well, this is going to be posted, what I'm doing right now.
Right. Okay.
Yeah, it'll be a video that you can watch. And in fact, yes, what I could do is I could print this as the notes as well. Would that be helpful? Okay. I can do that. Okay, matter. So to understand chemistry, which is the study of matter, well, now we have to define what matter is, because, well, what is the stuff that we call matter? Matter is anything that has mass and it occupies space. So everything we see around us, everything we can perceive is matter, because it's occupying space, it has mass, therefore it's matter. In fact, a lot of the stuff we can't see is matter. How about the air particles all around us? Does that matter? Oxygen that's around us, that we breathe? Yeah, that's matter, because it occupies space. It's very little bit of space, but it occupies space and it has mass. Okay, so I could measure how heavy a sample of air is. Well, that seems strange because, I can't just take it and put it on a scale, right? Well, or you're thinking, well, Mr. Crandall, you can't measure air. It floats. Well, air doesn't really float. It's that we sink, right? We're sinking in the air. If I stepped into water, I would sink in it. The water's not floating, right? It's just that the water is heavier than the air, so the water sinks in the air, and I sink in the water because I'm heavier, I'm more dense than the water. Okay, so it's all about density. So I'm more dense than the air around me. So the air isn't floating; it's just less dense than I am. So it does have matter. All the air particles have matter. They have mass. They occupy space. Okay, and then we're going to try to understand energy, which is the ability to do and accomplish work on something. So the transfer, and in chemistry it's heat energy. The transfer of heat energy from one source to another one. That's what we want to understand. And as you see, chemistry is involved in all kinds of fields. Public health, pharmaceutical, food science, forensic science, medical. They all deal with chemistry. So it's kind of a central science. Chemistry, it has a lot to do with biology, biochemistry. It has a lot to do with physics. Okay? So we call it that central science. It's kind of the bridge between physics and biology, basically. That chemistry right there in the middle. So to understand chemistry, we need to know some physics, and to understand biology, we really need to know some chemistry. So that's kind of the progression that we see. We're not going to spend a lot of time on the scientific method because this isn't a research course. So we're not going to really do much with that. Okay, models. In chemistry, we use models because models help us to perceive something. They help us to understand these molecules, because we deal with things that we cannot see. I cannot see a carbon atom. And I certainly can't see a carbon atom bonded to 4 hydrogen atoms. So what does that thing look like? Well, they've done lots of experiments to determine structures of molecules. And so now we can start to build models based on that experimental evidence of what these things look like. And now I can kind of see what it looks like. Oh, okay. So carbon is surrounded by 4 hydrogens. The hydrogens all separate around the carbon atom by by the same degree. Because they they push away from each other in the exact same distance. So if I tried to push this hydrogen closer here, it would just bounce back because the repulsion between between them would cause them to separate to these exact proportions. Okay? So this is just a model that we can see, we can perceive it. So we deal a lot with models so that we can try to understand the chemistry that's going on here. Okay. So matter is classified in these ways. We classify matter by its properties. Properties are the characteristics of matter that we can use to categorize the different matter, right? So we categorize it by its physical state and by its composition. What is it made of? Okay? So we can classify them in those ways. So these are the 3 states of matter. We have gas, liquid, solid. Okay? So gas particles, like the ones in this room, they're bouncing off the walls. They're not touching one another. They're not interacting. They might collide and bounce off of one another, but they don't stay stuck to each other. They have too much energy. And all that energy within them is causing them to just bounce everywhere. Okay? But if I start to cool the temperature in this room down, then what happens to the energy in those molecules? Well, here they are. They're going all over the place really fast, and I start to cool it down, and they slow down. Now they're not going as fast. And now when they find each other, they start to stick to one another. So I'll cool them down, and they start to stick. We're condensing them. They're condensing into a liquid. Okay? And as they condense into that liquid phase, now instead of breaking off from one another and bouncing off the walls, they condense, and they start just rolling over each other. Okay? They just roll over each other. And then, if we cool them down even more, we pull more energy off of them, instead of rolling over each other, then all of a sudden they get stuck in one position. We say that's a solid. Particles are close together, definite shape and definite volume. They've now stopped moving, they're stuck in fixed positions. So I shouldn't say stopped moving. It's not that they've stopped moving, they're still moving. They're just not moving around each other. But even when they're like this, in their fixed positions as a solid, they're vibrating. They're moving. Because they still have energy. So this table, it's a solid, but the particles within it are vibrating. They're vibrating in their fixed positions. How could I stop that? Anybody, any ideas? What would I have to do? So think of a piece of ice. It was a liquid. I freeze it. Ice freezes at 0 degrees Celsius, and it becomes a solid. Well, the particles in that piece of ice are doing this. How could I stop them from doing this? Okay, well, if I heat them up, then they'll start moving more. But we want to cause them to go like this, to stop moving at all. So at 0 degrees Celsius, they're going to freeze, and they're going to be like this. If I lower the temperature even more, they slow down. If I lower it even more, they get slower. What do you think I would have to reach? Absolute zero. I would have to get to all the way to the coldest temperature possible, which is absolute zero, in order for all motion to completely stop in those particles. Okay? That is the coldest temperature I can achieve. Absolute zero. No more motion. Okay? So that's, what is that? That's water freezes at 0 degrees Celsius, and absolute zero is in the Kelvin temperature, which is offset by 273 degrees Kelvin. Okay? So that means 0 degrees Celsius is 273 Kelvin. So to get to absolute zero, I have to get to negative 273 degrees Celsius. So that's how cold you would have to make it to cause all motion and all molecules to stop. Okay? So that's something they haven't really done yet, because that's nearly impossible to get that temperature. Okay? But that's what's happening in these phases. Okay? Okay. Now we want to classify this matter, okay, as pure substances or mixtures. So we have matter. We're going to divide them into two more categories. So anything that has mass and occupies space, we're going to divide it into two categories: pure substances or mixtures. Okay? A pure substance, this is always the one that people have the hardest with, because mixtures people understand pretty well. But pure substances is a substance that has only one component, and that definition is a little confusing. And the reason it's confusing is because it doesn't give a very good definition of what this is really is. Okay, so sodium chloride, NaCl, water, H2O, oxygen, O2. Which of those fall into this definition? A substance that has only one component. The answer is all three of them. See why it's confusing? Okay, so that's what I want to clarify. They're not saying one component is one element. Oxygen is an element, that would be one component. That's easy, I can understand that. But when it gets into water, well, water is a pure substance. Water is H2O, it's one thing. Okay? It is oxygen bonded to two hydrogens. It's just one thing. That's what it is. So, it's one substance. It is a pure substance. If I have water and it's pure water, that's considered a pure substance. If I dump some salt, sodium chloride, into that water, it becomes a mixture. Okay? So, why isn't my pen ready? Oh. My pen decided to die on me. Oh. Okay, so sodium chloride in the water would be a mixture of two pure substances. Two pure things put together. If I go take salt out of my cupboard, that's a pure substance. It's sodium chloride. It's a pure substance. And if I put it into the water, now it's a mixture of two pure things. Well, they're not pure anymore because I'm mixing them, right? But so that's how we need to understand this. Okay? That's how we need to understand what's going on between these two things. Oh, now it's working. Okay? Good. That's good. Okay. So, pure substance. Elements. Compound. Examples. Elements, oxygen, hydrogen. Compounds, salt and water. So those are all considered pure substances. Okay? A compound, a compound is the result from the combination of two or more elements, right? But it's still its own thing. Even a sugar molecule. A sugar molecule, it's a pure thing. I go to my cupboard, I get some sucrose out of the cupboard. That's a pure substance. Even though it's a gigantic molecule, I should say, not necessarily gigantic, but compared to like water, water is H2O. Okay? If you get a disaccharide sugar sucrose molecule, then that thing, well, even a glucose, let's just look at glucose, which is a monosaccharide. Okay? You know, that's what it looks like. That's way more complicated than H2O, right? But it's still a pure substance because it has its own identity. It's a glucose. It's a glucose sugar molecule. So it has its own identity. Okay, now mixtures. We have two categories of mixtures. We have homogeneous mixtures, homogeneous, or we have heterogeneous mixtures. So homogeneous meaning the same throughout, uniform composition throughout the entire thing, or heterogeneous meaning that it is non-uniform, a non-uniform composition. So if I take the salt water example, I have my water and I put some salt in it and I just leave it there. I come back the next day, what is going to happen? It will dissolve, right? Did I have to do anything? I just left it there on the table. I walked away. I came back, and it's clear. It's dissolved. The salt is gone. Well, it's not really gone. It's just now inside of the water. Okay? So if I take a sample of this dissolved salt water, okay, so let's get rid of the salt. It's a clear solution. The salt's in there. If I take a sample right here and right here, will it be the same? Will there be as much salt right here as there is right here? Yeah. There will be exactly the same amount of salt at the bottom as there is at the top. Because the particles separated themselves. I didn't have to do anything. They did it all on their own. They saw how close each other were, and they said, oh, that's too close, and now I'm too close to that guy, and they separate each other perfectly. Throughout the entire thing, they will separate themselves perfectly. Okay? That is a uniform composition. That's uniform. But if it's something where I am doing the mixing, so I take my lettuce and my tomatoes and my avocado and I mix it all together, can I guarantee there's as many tomatoes on this part of the salad as there is on this part? No way, right? It never happens. You're like, I have to have a perfect bite. That's how my wife is. I have to have the perfect bite. I have to have exactly one tomato. And she's like, it's so hard. Okay? That's because it's not, it doesn't separate itself. I'm doing the mixing. It's a heterogeneous mixture. Okay? No matter how much I sit there and mix that thing, it's never going to be perfect. It's not going to be perfect. Okay? So we say it's heterogeneous mixture, a non-uniform composition. Okay. So we have pure substances, we have homogeneous mixtures, and we have heterogeneous mixtures. So look at this rock right here. Right? You can see the discoloration in the rock through here. Basically through the whole thing. It's just different colors, right? That's because it's made up of different compositions of ionic salt particles, okay? And so we have one type here, we have another type over here, etc. That's a heterogeneous mixture. This thing is not uniform. It is not the same throughout, right? That rock. It's not. So it's heterogeneous. Here we have a mixture of probably something like copper chloride. Copper gives a nice blue color when you dissolve it into solution, okay? So it's a copper ion, meaning it's a charged copper particle. So it'll dissolve, and it's blue. And it is a solution. Those particles have separated themselves perfectly on their own, okay? So that's what we see here. The water and the copper, they're all mixed perfectly, even though they didn't do a very good job of that. But okay, they are mixed perfectly throughout. If I take a sample at the top and the bottom, it's the same. It is homogeneous mixture. Okay? And then here we have water as a pure substance. The water is a pure substance. Okay? Now, if I could dissolve the particles of this into the water, those particles would actually separate themselves perfectly, and then it would become homogeneous. Even though they're not homogeneous here, they would become homogeneous if they became a solution. Okay? Okay. Physical properties versus physical change. So we want to try to understand and identify. You're going to need to be able to identify the differences between something that is a physical property, a physical change, or a chemical property, or a chemical change. And chemical properties are basically the same as chemical change, because to observe a chemical property, it has to undergo a chemical reaction, which is undergoing a chemical change. Okay? So those two things relate. Physical properties and physical changes, not as much as with chemical. Okay? So a physical property is observed without changing the composition or identity of the substance. Physical change produces a recognizable difference without causing any change in the composition or identity. So that's how I'm going to know whether it's physical or chemical. If it changes its identity, that's a chemical change. But if it retains its identity, it's a physical change. Okay? So for example, going from one physical state to another one, melting an ice cube. So if you have H2O solid, which is ice, to H2O liquid, which is just liquid water, has it changed chemically? It is still H2O, right? There is no chemical difference between H2O solid and H2O liquid. It's exactly the same thing. So that is a physical change. It has undergone a physical change, not a chemical change, a physical change. So here we see that for water. You have ice, you have liquid water, and you have water vapor. It's a gas, which we have lots of outside right now. Right? So, but those are the three states, physical states, that water can go through. And anything can go through those three physical states. If I have a sample of oxygen, can I cause it to become a liquid? So it's a gas at room temperature, but I could cool it down enough to make it liquid oxygen, right? I could even cool it down enough, if I could get this low of a temperature, I could cool it down enough and make it a solid oxygen. Okay? Have you guys ever seen the space shuttle, the big orange tank on the middle of it? That thing is full of liquid oxygen and liquid hydrogen, because the space shuttle fuel is hydrogen plus oxygen to react to form water. Liquid oxygen, liquid hydrogen on the space shuttle tank. Okay? That's its fuel. So there you go. You guys are rocket scientists. I always like you're not a rocket scientist. It's not that hard. Oxygen, hydrogen, rocket fuel. Okay? That's what it is. Form water. Okay? H2 plus O2. So But I could cause anything to go through those states of matter. Can I cause a piece of rock to melt? Have you ever seen a volcano? What happens? It erupts, and what spews out of it? Lava. And what does that lava do when it hardens? It's rock, right? So, under the crust of the earth, just a bunch of molten rock, right? We live on our Earth's crust, which is a thin layer of the earth, and everything else under it is just a bunch of molten stuff, right? And so sometimes through a volcano that will come spewing out and, hardens into rock here on the surface. So, yeah, we could make that molten. We can make it liquefy. So those, and I could even, if I get to a high enough temperature, I could make it evaporate. Okay, it would evaporate into gases. So if our Earth is traveling towards the sun, we're not going to hit the surface of the sun. We're going to just completely evaporate because the sun is the temperatures of the sun are way too great for us to even consider getting close enough to collide into it. Okay, so we would just evaporate. Everything would just evaporate into its gas components. All right, and so the sun's not too worried about that. Okay, so with these mixtures. Okay, if we have mixtures are a combination of substances that are combined physically. They're combined physically. So that means I can separate them. I can separate them by physical means. So here we see iron mixed with sand. What type of mixture? Homogeneous, heterogeneous. What do you think? So can I guarantee there's the exact same amount of iron here as there is here? No. I can sit there and mix that thing all day if I wanted to, and I would never guarantee that it is a homogeneous mixture, that the composition throughout the entire thing is exactly the same. It's not going to happen. Okay? Because are the particles mixing themselves? No. Nope. They would do a perfect job if they were, but they're not. Okay? So if I do the mixing, it's heterogeneous. This is a heterogeneous mixture. Iron and sand. Iron is magnetic, sand is not. Those are two physical characteristics that are different about these things. So I can separate them by taking a magnet and pull out the iron. I physically have separated them. Okay? So any mixture that is physically mixed can be separated by physical means. But if you combine things chemically, you cannot separate them by physical means. You have to use what type of means? Chemical. If I take hydrogen and oxygen and react it to form water, then to break that back down, I have to use chemical means to break it back down into hydrogen and oxygen. So physical means can separate physical mixtures. Chemical means can separate chemical combinations, which are not mixtures, they're pure substances, right? Okay. So chemical properties result in chemical changes. It has changed its identity. Okay, and we observe it through chemical reactions. Hydrogen plus oxygen, H2 plus O2 forms H2O. Hydrogen plus oxygen forms water. This hydrogen has changed its identity. It is no longer hydrogen, it is water, part of water. The oxygen has changed its identity. It is no longer oxygen, it is now part of water. Okay? So they have become something different. And whenever you become something different, you have undergone a chemical change. You've undergone a chemical change. And the only way I can reverse that is through chemical means. This is not a mixture. It is a pure substance. Because these are no longer there. All I have left is this. I just have water. It's a pure substance. Okay. Now, if I did have something over here left, then yeah, it wouldn't be a pure substance because I'd have this and this mixed together. Okay. All right, let's classify these. Classify the following as either a chemical or physical property. Color. That's a physical. It's a physical property. Flammability. Good. If I burn something, what am I burning it with?
Fire.
Okay, well, it creates the result of that chemical reaction results in heat and light, which is a flame, which is fire. But what am I in the air? If I light a piece of wood, that wood is burning with what? Oxygen. It's burning with oxygen. So if something's flammable, that's because it will react with the oxygen in the air and it will burn. And that we could say that that's combustible. Okay? So combustion is when you react something with oxygen. Hardness. Physical. They always get me on these ones because odor. Okay, yes, I would say that that is chemical because if I smell something, why does it smell the way it smells? Because of its chemical composition. Cinnamon has a very distinct smell because it has a very distinct chemical composition that our nose recognizes as the smell of cinnamon. Okay, so it's receptors that are interacting with those chemicals. Those same receptors something else won't interact with them. So it's a chemical interaction it is undergoing. However, is it changing its state? Is it becoming something different?
No.
Or is it still cinnamon? Still cinnamon. So yeah, you could definitely argue that this is a physical interaction because of its physical nature, of the way it is. That's, it's not changing. It's not undergoing a chemical reaction. It's just being recognized. Okay, so yeah, I have a hard time with arguing against either one of those. Okay, so for both odor and taste, it's basically the same. So I need to update that example. I don't like it. Okay, this one's better. Classify the following as either chemical or physical. Boiling water becomes steam.
Physical.
That's physical. Good. Butter becomes rancid.
Chemical.
Okay, so the butter was one thing, and then the bacteria got in there. They started, making it rancid, and they changed it. They changed it into something different. So now it is chemically changed. Okay? Burning of wood. Chemical. So these are key words, right? Burning, that would be a key word. Mountain snow melting in spring. It just sounds so poetic. Okay, that's a physical. Decay of leaves in winter. Good. Decay. They are decaying. It is this organic leaf molecule, and they decay it into its components, nitrogens and carbons, and they just break it down into the soil. Okay? So yes, that becomes something different. It is a chemical, It is a chemical change that it undergoes. Okay. 2 vocabulary words. intensive property and extensive property. So these are not difficult because the name gives you the answer. What is an intensive property? It is independent. An intensive property is independent. Okay? It is independent of the amount of matter that you have. An extensive property is therefore dependent. So as long as you understand intensive is independent, then you will know that extensive is dependent. Okay? Intensive, independent. Extensive, dependent. Well, what does that mean? It means that if I have a cup of water, and then I get a smaller cup, and I put some of that water in here, the density of this water, let's say, is equal to 0.996 grams per milliliter. Has that density changed when I put it in that cup? If I take a sample of this and put it in here, has the density of the water changed? Not at all. The density is still 0.996 grams for every milliliter. It is exactly the same because density is a ratio. So what type of property is that? What is it? Intensive. It is independent on the amount. Doesn't matter how much I have, the density will be the same. If I have a block of wood and I cut it into 2 pieces, has the density of this wood changed? No. Has the mass of it changed? So is mass intensive or extensive? Extensive. Mass is dependent on how much you have. The more I have, the heavier it is. The less I have, the lighter it is. Okay? And with that, we'll see you guys next time.